Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Lee Lorch's Life Charts, a fascinating course, deeply intertwined with the evolution of 20th century mathematics, and though we will explore that later, the shifting sands of social justice. This initial exploration focuses on the formative years, tracing his path from early education to his emergence as a promising mathematician specializing in summability theory. His intellectual journey began far from the lecture halls he would later grace, laying the foundation for a career marked by both mathematical rigor and a commitment to principles. Born in New York City in 1915, Lorch demonstrated an early aptitude for mathematics. His undergraduate studies at Cornell University provided a fertile ground for cultivating his intellectual curiosity. He excelled, absorbing the foundational principles that would underpin his future research. This period was marked by a dedication to mastering the intricacies of mathematical analysis, setting the stage for his graduate work. Lorch pursued his doctoral studies at the University of Cincinnati, a period that proved pivotal in shaping his mathematical focus. Here he encountered the area of summability theory, a field that offered a unique blend of analytical challenges and profound theoretical implications. He found himself drawn to its intricacies, embarking on a path that would define his early career. Summability theory, at its core, grapples with the challenge of assigning meaningful values to divergent series. These series, which do not converge in the traditional sense, arise naturally in various branches of mathematics and physics. Consider, for instance, the series 1 minus 1 plus 1 minus 1, and so on, ad infinitum. This series oscillates endlessly, never settling on a definite sum in the conventional understanding of convergence. Yet such series often emerge as solutions to differential equations, or in the context of Fourier analysis, demanding a method for interpretation and manipulation. The challenge lies in devising consistent and useful methods for assigning values to these divergent series. A summability method is, in essence, a transformation that maps a divergent series to a finite value, effectively summing the series in a generalized sense. However, the key is to ensure that such a method remains consistent with the classical notion of convergence. That is, if a series converges in the usual sense, the summability method should assign it the same value. Numerous summability methods exist, each with its own strengths and weaknesses. Cicero summation, for example, takes the average of the partial sums of a series. Abel summation, on the other hand, considers the limit of a power series as the variable approaches 1. The choice of method often depends on the specific properties of the series in question and the desired application. Lorch's early work in summability theory focused on refining and extending these existing methods. He sought to develop new techniques that could handle a broader class of divergent series, while simultaneously preserving the desirable properties of consistency and regularity. His initial publications demonstrated a deep understanding of the underlying principles of summability, coupled with a remarkable ability to devise innovative solutions to challenging problems. One particular area of focus involved Tauberian theorems. These theorems provide a link between the summability of a series and its ordinary convergence. They essentially state that if a series is summable by a particular method, and if it satisfies certain additional conditions, then it must also converge in the usual sense. The problems Lorch tackled within summability theory were far from abstract exercises. They represented genuine attempts to grapple with the complexities of infinite processes and to develop tools for making sense of divergent phenomena. His work contributed to a deeper understanding of the nature of convergence and divergence, providing mathematicians and physicists with a powerful arsenal for analyzing complex systems. His initial forays into the world of mathematical research demonstrated not only technical skill, but also a keen eye for identifying important problems and a relentless pursuit of elegant solutions. This early work established him as a significant voice in the mathematical community, setting the stage for further contributions in diverse areas of mathematical analysis. The foundations laid during these formative years would support a career marked by intellectual curiosity and a dedication to advancing mathematical knowledge. The investigations into infinite series and their summability properties provided a springboard for Lorch's subsequent explorations in the realm of differential equations and orthogonal polynomials. This transition reflects a natural progression within mathematical analysis, as the behavior of solutions to differential equations is often intimately linked to the convergence properties of associated series expansions. Differential equations, the language in which many physical laws are expressed, became a central focus of his research. A significant portion of Lorch's work in this area centered on the zeros of solutions to differential equations, particularly their distribution and interlacing properties. Consider a second-order linear homogeneous differential equation of the form y double prime plus p of x times y prime plus q of x times y equals 0, where y double prime denotes the second derivative of y with respect to x, y prime denotes the first derivative, and p of x and q of x, or continuous functions. Such equations arise ubiquitously in physics and engineering, modeling phenomena ranging from the vibrations of a string to the flow of heat. Lorch investigated the location and separation of the points where solutions to these equations vanish, the zeros of the solutions. He sought to establish relationships between the zeros of different solutions and to understand how these zeros behave as parameters within the equation are varied. This line of inquiry is deeply connected to the eigenvalues of associated Sturm-Liouville problems. A Sturm-Liouville problem involves solving a differential equation subject to certain boundary conditions. The solutions exist only for specific values of a parameter known as eigenvalues, and the corresponding solutions are called eigenfunctions. The eigenvalues of a Sturm-Liouville problem are intimately related to the oscillatory behavior of the solutions. Lorch's work revealed how the distribution of zeros of solutions to the differential equation is intertwined with the eigenvalues of the corresponding Sturm-Liouville problem. He demonstrated that the eigenvalues dictate the density and spacing of the zeros, providing valuable insights into the qualitative behavior of solutions. One specific problem he addressed concerned the interlacing of zeros. Given two linearly independent solutions, y1 of x and y2 of x, to a second-order linear homogeneous differential equation, Lorch investigated whether the zeros of y1 of x necessarily lie between the zeros of y2 of x, and vice versa. This property, known as interlacing, provides a powerful tool for understanding the oscillatory behavior of solutions. He established conditions on the functions p of x and q of x that guarantee the interlacing of zeros, providing a deep understanding of the qualitative properties of solutions without explicitly solving the equation. His approach often involved a combination of analytical techniques, including careful estimates of integrals, comparison theorems, and asymptotic analysis. He developed ingenious methods for bounding the number of zeros in a given interval and for determining the asymptotic behavior of zeros as the independent variable tends to infinity. These techniques allowed him to extract valuable information about the solutions even when explicit formulas were unavailable. Beyond differential equations, Lorch also made substantial contributions to the theory of orthogonal polynomials. Orthogonal polynomials are sets of polynomials that satisfy a certain orthogonality condition with respect to a given weight function. That is, the integral of the product of any two distinct polynomials in the set, multiplied by the weight function, is 0. These polynomials arise in various areas of mathematics, physics, and engineering, including approximation theory, numerical analysis, and quantum mechanics. He explored inequalities involving orthogonal polynomials, seeking to establish bounds on their values and their derivatives. These inequalities provide crucial information for understanding the behavior of orthogonal polynomials and for using them in approximation schemes. He also investigated the asymptotic behavior of orthogonal polynomials, determining how they behave as the degree of the polynomial tends to infinity. This asymptotic analysis is essential for understanding the convergence properties of series expansions involving orthogonal polynomials. For example, consider the classical orthogonal polynomials such as Legendre polynomials, Hermite polynomials, and Laguerre polynomials. These polynomials are solutions to specific Sturm-Liouville problems and possess a rich set of properties. Lorch's work provided valuable insights into the behavior of these polynomials, including their zeros, their inequalities, and their asymptotic behavior. His contributions extended to weighted polynomial approximation. In weighted polynomial approximation, the goal is to approximate a given function by a polynomial, where the error is measured with respect to a weighted norm. The weight function reflects the importance of different regions of the domain. Lorch's work provided a theoretical foundation for understanding the convergence properties of weighted polynomial approximations, with implications for numerical analysis and scientific computing. The significance of Sturm-Liouville problems and orthogonal polynomials extends far beyond pure mathematics. These concepts are ubiquitous in applied mathematics, physics, and engineering. In quantum mechanics, the solutions to the Schrödinger equation, which describes the behavior of quantum particles, are often expressed in terms of orthogonal polynomials. The eigenvalues of the Schrödinger equation correspond to the energy levels of the quantum system, and the eigenfunctions describe the probability amplitudes of the particle. In signal processing, orthogonal polynomials are used to represent and analyze signals. For instance, Legendre polynomials are used in the design of filters and antennas. The properties of orthogonal polynomials, such as their orthogonality and their completeness, make them well suited for representing signals in a compact and efficient manner. Moreover, in engineering, Sturm-Liouville problems arise in the analysis of vibrations, heat transfer, and fluid flow. The solutions to these problems provide valuable insights into the behavior of physical systems and are used to design and optimize engineering structures. For example, the natural frequencies of a vibrating beam are the eigenvalues of a Sturm-Liouville problem, and the corresponding eigenfunctions describe the mode shapes of the beam. Lorch's work on differential equations and orthogonal polynomials continues to resonate within the mathematical and scientific communities. His insights into the zeros of solutions, the interlacing properties, and the asymptotic behavior of orthogonal polynomials have had a lasting impact on the field. These concepts, initially explored in the abstract realm of mathematical analysis, find concrete applications in diverse areas of science and engineering. The enduring relevance of his contributions underscores the power of fundamental mathematical research to illuminate the complexities of the physical world. The elegance and depth of his work serve as a testament to the beauty and utility of mathematics. Lorch's mathematical investigations, while contributing significantly to analysis and its applications, existed alongside a deep commitment to social justice, a commitment that would ultimately lead to significant challenges in his academic career. The post-Mainz World War II era in the United States was marked by both unprecedented economic growth and a pervasive atmosphere of political suspicion. The rise of McCarthyism, named for Senator Joseph McCarthy, created a climate of fear and repression, where accusations of communist affiliation, often unsubstantiated, could ruin careers and lives. Academic institutions, traditionally seen as bastions of free thought and open inquiry, were not immune to this pressure. Lorch's outspoken advocacy for civil rights and his defiance of segregationist practices placed him squarely in the crosshairs of this political climate. His troubles began in 1949, shortly after he accepted a position at City College of New York. The college, a public institution with a long history of serving immigrant and working-class students, found itself under increasing scrutiny from conservative politicians and media outlets due to its perceived radical leanings. Lorch's activism, including his participation in protests against racial discrimination and his support for progressive causes, drew the attention of college administrators and trustees. The specific incident that triggered his dismissal from City College involved his efforts to integrate a swimming pool in Stuyvesant Town, a newly built residential complex in New York City. Stuyvesant Town, developed by the Metropolitan Life Insurance Company with public funds, maintained a strict policy of racial segregation. Lorch, along with his wife Grace, actively campaigned against this discriminatory practice, organizing protests and challenging the legality of the segregation policy. Their efforts, while ultimately successful in desegregating the housing complex, made them targets of intense criticism and harassment. The pressure on City College to take action against Lorch intensified, fueled by newspaper articles and political pressure. Despite some faculty members rallying to his defense, the college administration ultimately decided to terminate his appointment, citing budget cuts as the official reason. However, the timing of the dismissal, so soon after the Stuyvesant Town controversy, made it clear that his political activities were the primary cause. The loss of his position at City College was a significant blow, but Lorch remained undeterred in his commitment to social justice. He secured a position at Pennsylvania State University, where he continued his research in mathematical analysis. However, his past activism continued to haunt him. In 1954, he was called to testify before the Senate Internal Security Subcommittee, a congressional committee investigating alleged communist influence in educational institutions. During his testimony, Lorch refused to answer questions about his political affiliations, invoking his Fifth Amendment rights. This refusal, while legally protected, further fueled the suspicions against him and led to renewed calls for his dismissal from Pennsylvania State University. The university administration, facing intense pressure from state legislators and conservative groups, ultimately decided to suspend him without pay. This action effectively terminated his employment, as he was unable to support himself and his family without a salary. The circumstances surrounding Lorch's dismissal from Pennsylvania State University highlight the chilling effect of McCarthyism on academic freedom. The university, rather than defending his right to express his political beliefs, succumbed to political pressure and sacrificed his career. This decision sent a clear message to other academics that expressing dissenting views could have dire consequences. Following his dismissal from Pennsylvania State University, Lorch faced considerable difficulty finding another academic position in the United States. His reputation had been tarnished by the accusations of communist affiliation, and many institutions were hesitant to hire someone who had been labeled a security risk. He eventually accepted a position at Philander Smith College, a historically black college in Little Rock, Arkansas. Philander Smith College, despite its limited resources, had a strong commitment to social justice and a tradition of academic freedom. Lorch found a supportive community there and continued his work in mathematics. However, his presence in Little Rock coincided with the escalating crisis over school desegregation. In 1957, Governor Orval Faubus defied a federal court order to desegregate Little Rock Central High School, sparking a national crisis. Lorch and his wife actively supported the efforts to integrate the school, providing assistance to the black students who were attempting to attend. Their involvement in the desegregation struggle again made them targets of harassment and intimidation. The local white community, deeply resistant to integration, viewed them with suspicion and hostility. The pressure on Philander Smith College to dismiss Lorch intensified, fueled by the racial tensions in Little Rock. The college administration, facing threats of violence and economic retaliation, ultimately decided to terminate his appointment. This decision, while understandable in the context of the extreme pressure the college was under, was another blow to Lorch's career and a further demonstration of the challenges faced by academics who dared to challenge the status quo. The series of dismissals Lorch faced raises profound ethical questions about academic freedom and the responsibilities of academics in engaging with social issues. Academic freedom is often defined as the right of teachers and students to discuss and explore ideas relevant to their field of study without fear of censorship or retaliation. This freedom is considered essential for the pursuit of knowledge and the advancement of learning. However, the case of Lee Lorch demonstrates that academic freedom is not always guaranteed, particularly when academics express views that are unpopular or challenge established power structures. The McCarthy era created an environment where academic freedom was severely curtailed, and many academics were silenced or punished for their political beliefs. The question of the responsibilities of academics in engaging with social issues is also a complex one. Some argue that academics should remain neutral and objective, focusing solely on their research and teaching. Others believe that academics have a moral obligation to use their knowledge and expertise to address social problems and advocate for justice. Lorch clearly belonged to the latter camp. He believed that his mathematical skills and his position as an academic gave him a platform to speak out against injustice and to work towards a more equitable society. He saw his activism as an integral part of his intellectual and moral life. The suppression of dissenting voices in academia, as exemplified by the case of Lee Lorch, has significant implications for the health and vitality of intellectual discourse. When academics are afraid to express their views, it stifles creativity, limits the range of perspectives considered, and ultimately hinders the pursuit of truth. Academic censorship can also have a chilling effect on students, discouraging them from engaging in critical thinking and challenging established ideas. The problems of academic censorship and the suppression of dissenting voices remain relevant today. While the McCarthy era has passed, there are still instances where academics face pressure to conform to certain political or ideological viewpoints. It is crucial to defend academic freedom and to create an environment where academics can express their views without fear of reprisal. The pursuit of knowledge requires open inquiry, critical thinking, and a willingness to challenge the status quo. The story of Lee Lorch serves as a cautionary tale about the dangers of political repression and a reminder of the importance of defending academic freedom. Following years of enduring political persecution and facing persistent obstacles to his academic career within the United States, Lee Lorch embarked on a new chapter in Canada. This move marked a significant transition, leading him to York University in Toronto, where he found a more welcoming environment to continue his mathematical work and advocacy. At York University, Lorch dedicated himself to teaching and research, further solidifying his reputation as a respected mathematician. He became deeply involved in mathematics education, recognizing the importance of making mathematical concepts accessible to a wider audience. His focus extended beyond the theoretical realm, encompassing a practical commitment to improving the learning experience for all students. Lorch's contributions to mathematics education were particularly notable for his efforts to promote access to mathematics for underrepresented groups. He understood that systemic barriers often prevent marginalized communities from fully participating in mathematical pursuits. He actively worked to dismantle these barriers, advocating for inclusive teaching practices and creating opportunities for students from diverse backgrounds to excel in mathematics. His dedication to equity and inclusion transformed the landscape of mathematics education, inspiring countless students and educators to challenge existing inequalities. Lorch championed innovative pedagogical approaches, emphasizing conceptual understanding over rote memorization. He believed that students should engage with mathematics in a meaningful way, developing a deep appreciation for its beauty and power. His teaching methods encouraged critical thinking, problem-solving skills, and a collaborative learning environment. Students thrived under his guidance, developing a lifelong love of mathematics. Beyond his contributions to mathematics and education, Lorch remained steadfast in his commitment to social justice. He continued to advocate for equality and human rights, using his platform to speak out against injustice wherever he saw it. His activism extended beyond the academic sphere, encompassing a wide range of social and political issues. He understood that mathematics could be a powerful tool for social change, empowering individuals to analyze data, identify patterns of inequality, and advocate for evidence-based solutions. Lorch's unwavering dedication to social justice reflected his deep-seated belief in the inherent dignity and worth of every human being. He challenged systems of oppression and discrimination, working tirelessly to create a more just and equitable world. His activism was not merely a matter of personal conviction. It was an integral part of his identity as a mathematician and educator. He saw his work as a way to contribute to the betterment of society, using his skills and knowledge to make a positive impact on the lives of others. Examining the multifaceted career of Lee Lorch reveals a remarkable synthesis of intellectual pursuits, political engagement, and unwavering commitment to social justice. His story transcends the boundaries of traditional academic disciplines, offering a profound reflection on the role of intellectuals in society. Lorch demonstrated that academic excellence and social responsibility are not mutually exclusive, they are in fact mutually reinforcing. His life serves as an inspiration to scholars and activists alike, demonstrating the power of knowledge to transform the world. The enduring relevance of Lorch's story lies in its powerful message about the importance of academic freedom, social responsibility, and the pursuit of knowledge. His experiences during the McCarthy era serve as a cautionary tale about the dangers of political repression and the suppression of dissenting voices. His unwavering commitment to social justice reminds us that intellectuals have a moral obligation to speak out against injustice and to use their knowledge to promote equality and human rights. Lorch's legacy extends far beyond his specific mathematical contributions. He represents a model for socially responsible scholarship, demonstrating the transformative power of knowledge when combined with a deep commitment to ethical principles. His life challenges us to consider the broader implications of our work, to engage with the world around us, and to use our skills and knowledge to create a more just and equitable society. Consider the implications of Lorch's advocacy for access to mathematics for underrepresented groups. He recognized that mathematical literacy is essential for success in the modern world, empowering individuals to participate fully in the economy, to understand complex social issues, and to make informed decisions about their lives. By working to dismantle barriers to mathematical education, Lorch helped to create opportunities for marginalized communities to thrive. His efforts continue to inspire educators and policymakers to address systemic inequalities in education and to ensure that all students have the opportunity to reach their full potential. Also, contemplate Lorch's dedication to innovative teaching methods. He understood that traditional pedagogical approaches often fail to engage students in a meaningful way, leading to disinterest and a lack of understanding. By emphasizing conceptual understanding, critical thinking and collaborative learning, Lorch created a more stimulating and effective learning environment. His teaching methods serve as a model for educators who seek to transform the classroom into a space for intellectual exploration and discovery. The interconnectedness of Lorch's mathematical pursuits and his unwavering commitment to social justice is a defining characteristic of his legacy. He saw mathematics as a tool for understanding the world and for addressing social problems. He used his mathematical skills to analyze data, identify patterns of inequality, and advocate for evidence-based solutions. His approach demonstrates the power of interdisciplinary thinking and the importance of connecting academic knowledge to real-world issues. Lorch's story is a testament to the enduring power of the human spirit. Despite facing adversity and political persecution, he remained steadfast in his commitment to his principles. His courage and resilience serve as an inspiration to all who strive to make a positive impact on the world. His life reminds us that the pursuit of knowledge is not merely an intellectual exercise, it is a moral imperative. In conclusion, Lee Lorch's life exemplifies the ideal of the socially responsible scholar. His mathematical contributions, his political activism, and his dedication to mathematics education are all interconnected, reflecting a deep-seated commitment to justice and equality. His legacy challenges us to embrace our responsibilities as intellectuals, to use our knowledge to promote positive change, and to stand up for what is right, even in the face of adversity. He leaves an indelible mark on the world, inspiring generations of mathematicians, educators and activists to strive for a better future. His story is a reminder that the pursuit of knowledge is inseparable from the pursuit of justice.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.